Okay, good morning everyone. So today we're going to learn about Kirchhoff law. There are actually two Kirchhoff law that I have to remember. Okay, so let's see what is the Kirchhoff law, the first. So Kirchhoff law, the first we call as junction on current law. It states that the sum of the current entering any junction in the circuit must be equal to the sum of current leaving that junction. Or we can say that is, if you can say in the mathematically form, is summation of I in current goes in equals to the total of the current that going out. So actually it's very analogous to a water. Okay, if you have a pipe of water, okay, let's say water came from three pipes of water. So I say this is I1, this is I2, and this is I3. So if the pipes of water are combined, okay, and then in some way it was separated into, okay, so this is we call as I4, and this is I5. So logically we can say that if there are same amount of current that goes in, is same amount of water goes into this junction and goes out in this junction, we can say that I1 plus I2 plus I3 will be equal to if I4 plus I5. This is very logic. If we have some amount of current goes to the junction, of course when you're leaving out the junction, it will be same as before. Okay, so one more example is if we have one pipes of water going in and it was separated into three, so this is I2, this is I3, and this is I4. So you can say that I1 will be equal to I2 plus I3 plus I4. Okay, this is very logical statement. Okay, this is Kirchhoff's law. And so if we have example, so you have a A here, junction of A, pick another color, junction of A over here. A junction is when two or more wires are intersect, okay, or separated, combined or separated. So if a junction over here, I2 and I1 is combined, okay, add up, you have I3. And this I3, when it goes to the other side, when you have a junction, it will be separated to I4 and I5. So biologically, you can say that I1 plus I2 equals to I3, and I3 also is equal to I4 and I5. Okay, so this is the Kirchhoff law for the first one. Second law, we call as a loop of voltage law. It says that in any loop, the sum of EMF is the source of the current. It can be a battery, it can be a solar, anything that contains EMF. The pushing force for the current is equal to the sum of the products of current and resistance. Or in any loop, summation of EMF equals to summation of IR. Remember, V equals to IR. So this is actually meaning of V. So actually, if we can change the statement, we can say that products, the current of some EMF, the sum of EMF is equal to sum of the products of voltage drops, because you have a voltage here. Voltage drops among the resistor in the circuit. Okay, in the circuit. So okay, so so you can see that if we have a statement over here, sign convention, of course EMS we have sign convention. So if for EMF, you have a direction of loop, you have a sign. If the current is flowing on the same way of the E, okay, direction of a loop, and direction of loop will be negative. So here we have direction of loop. Okay. Okay, direction of loop depends on the current moving. Okay, it can be a negative, it can be positive. Okay, depends on the arrangement of the battery. So the product of IR, or we call as voltage drops. Okay, the direction of it depends on the direction of loops. So it can be plus IR, it can be plus negative IR, depends on the current, where the current is moving. We're going to explain this when we have the real example. So the main general way to solve solve the problem for Kirchhoff law is first is to choose and label the current at each junction in the circuit given. The second step is choose any one junction in the circuit and apply the Kirchhoff first law, and choose any two closed loop in the circuit and designated a direction clockwise or anti-clockwise to travel around loop in applying Kirchhoff's second law. Okay, solving simultaneous equation. This is the last part where you have to determine what is unknown. It can be the value of first current I1, I2, I3, or it can be the EMF that is inside the battery. Okay, so for this we consider, let's say consider a circuit in this figure that is 18.27a. So you can see there in this circuit there are 1, 2, 3, 3 EMF. Okay, I label out the EMF. So this is first EMF. The positive are pushing are on the left side, okay, and negative on the right side. Second EMF is in the middle of the circuit, okay, and the positive are on the right side and negative on the left. And we have EMF number 3 over here, positive on the left side, negative on the right, negative on the left side, positive on the right side. And we have also contain 3 resistor, R1 over here, R2 over here, and R3 over here. So the first strategy is to determine where is the current that flows in the line of the battery or EMF. So the first one, you can see that the from here we have the current that flows in this direction for the first line, and second line we have a current because of the arrangement of the battery that is pushing to the right. Okay, and one more at the third line we have the current is pushing also to the right direction. Okay, so if we can make a loop, okay, this is a loop must contain one continuous circle, okay, over here. So you can see that there will be a loop over here, it's pushing over here and then goes to the second line and then goes back to the first line over here. So this is first loop. The second loop is from I take from E3 is vector EMF of E3, and it goes over here and then goes up, joining E1, and then goes down and goes back to the E3. Okay, so how about the third loop? Okay, this is the second loop. The third loop will be looks like this. From EMF E2 it goes to this side, first, second, and no, it goes over here. Okay, but this is moving in the negative direction. Okay, negative EMF. So you can see that the loop will be looks like this. Loop number 1. and then loop number 2. Okay, and loop number 3 is the big one as I draw before. Okay, so we're going to we're going to use the Kirchhoff law to make an equation, first and second equation on all of the loops. So loop number 1 we make equation of loop number 1, and then loop number 2 we make equation of loop Kirchhoff law loop number 2, and loop number 3 we make a equation on Kirchhoff loop number 3. So at junction A or D, applying Kirchhoff's first law, summation of in total current goes in equals to total current goes out. So I1, you can see that I1 over here, this is I1, or this one is I1, is equals to I2 plus I3. So remember, I1 goes to I2. This is a junction. This is I2, so this is I3. So logically, as I said, Kirchhoff's law, I2 plus I3 equals to I1. Okay, so this is goes in. If I draw in this way, this is goes in and this is goes out from the junction. Okay, so for the closed loop, either clockwise or anti-clockwise, apply the Kirchhoff's second law from loop 1. Still we are focused on the loop number 1. So for the loop number 1, okay, we can see that the current are flowing in counterclockwise. Okay, so we're going to make an equation of Kirchhoff law. So summation of E equals to summation of IR. This is second law. Okay, so E1 plus E2, because this is the sources. Okay, this is a voltage drop. Voltage drop means that how much the voltage has been taken out by the resistor. Okay, okay, so I2 and I2, so this is all the sources. This is I1 and I2. This is plus because they have the same direction of current. Okay, and I1 plus I2 R2, so I2 R2 this side, I2 R2, so this is IR equals how much of voltage drop over here, and I1 R1, this is how much of voltage drop over here. So how much of voltage V1, V2, V3, V3 is equals to E1 plus E2. From the loop number 2, A, B, C, D, A, okay, so the direction, can see that there are some difference from the first loop. You can see that is E2 minus E3. It's minus because the direction of both of them are not in the same. E2 and E3, they are producing current that is not in the same direction. Okay, they are opposed. So I2 R2 and minus I3 R3. Okay, so I2 R2, how much of voltage drop over here, minus I3 I3, I3, how much of voltage drop over here. Okay, V over here. So this one we call as equation number 3. So loop number 3 is the big one, the outer parameter of the circuit. Okay, so it is E1 plus E3. It's because they have the same direction of current flow, equals I3 R3 plus I1 R1. So how much the voltage drop over here, this side, and how much voltage drop over this side. Okay, by solving equation 1 and any two equations from the closed loop, hence the current in the circuit can be determined. Okay, so from the calculation, sometimes we get negative value of the current. This negative sign indicates that the direction of the actual current is opposite to the direction of the current drawn. Okay, so let's say we have some situation where the current is from the loop, the current is going in the loop that we make, the current is going in counterclockwise, but when we have I is value have a negative value, it means that the current is not moving in the counterclockwise, was moving in opposite direction. It means that it was moving in the one current we are measuring is moving in the opposite direction. Maybe it's going to the left. Okay, so let's say we have, for example, here this is more basic example than before. We have 2 EMF that is 11.5 volt, okay, with 2 ohm internal resistance, and we also have EMF one more over here, 15.0 volt with 4 ohm as the internal EMF, and we also have 1, 2 and 3 resistor. So determine the current and its direction in the circuit. Okay, first of all, we can see that both of the EMF over here, both of the battery, they are the current that flows from out of the both of the battery are in the same direction. So we can say that the loop will be like this, counterclockwise. Okay, so loop will be in counterclockwise. So we have now we're going to make a equation out of it. By applying Kirchoff's second law, thus E summation of E total E equals to total IR. So 15, you see that 15 plus 11.5, because both of them are in the same direction, equals to 15.1 I, 15, so this is IR actually, IR, or this is the value of R actually, this is I. We only have one I over here, one value of I, because there are no junction in this example. So I. So 15.1 I, 6.22 I, 2 I, which are the value of the resistor, 8.50 I and 4 I. So current in this circuit is 0.74 ampere. Okay, so it is moving in, the current are moving in anti-clockwise. If the, let's say if the when we calculate the I given is negative 0.74 ampere, it means that the current that we are measuring are actually in the opposite direction, maybe going in the clockwise direction. Okay, next example we have here, we have two EMF, one over here, resistor 1, 2, 3, 4 resistor. So because we have two loops, okay, two loops over here, you can see that they have two loops. Okay, so the current I1, I2 and I, so you can see that it's moving in this way, first loops, and second loop is moving in this way, second loop. So this is loop number 1, this is loop number 2. For currents I, I2 and I, so this is I, you can see that the I1 over here, this is I2 over here, this is I. Okay, so it's easy for you to find out how much is the I1, R2, I3. The potential difference across 6.7 resistor. So 6.7 resistor, how much the V over here, and V equals to IR. You get the I2, you get the R, you can get the value of the potential drop. The power dissipated from the 1.2 ohm resistor. So 1.2 ohm resistor over here, how much the power? P equals to IV. Okay, or P equals to IV and V equals to IR. So I squared R. Right. Okay, so you have the current from I, and you have the value of R, that is 1.2 ohm, and then you can get the power dissipated for the resistor. Okay, let's check the working. So it goes back to the solution. Okay, so loop number 1 and loop number 2. Okay, so at junction A, by using Kirchoff's first law, thus summation total of current in equals to total of current out. So I1 plus I2 equals to I. By using the Kirchoff's second law from loop number 1, summation of supply voltage or EMF equals to total of voltage drop IR. So 12 equals to 3.9 I1. You see, this is very important. You have to rename the the current that flows in that resistor. So 3.9 I1, remember, because 3.9 over here was the resistor was the current I1 was flown in the resistor 3.9 ampere ohm. So use I1, and 1.2 I over here is 12 over here, so it's the current that flows through the resistor is I only. Okay, so you have to remember, don't make a mistake on this part. So 12, and you have second equation. So this is the second equation. Okay, later on we're going to use a simultaneous equation for solving the answer, getting out the answer. So you have summation of E equals to summation of IR 9.0. Then you have the third equation, and when you do all the simultaneous equation, you can get the V. Okay, you can get the current of I1, that is 0.72, I2 1.03 ampere, and I 1.75 ampere. The potential difference across the resistor given V equals to IR. Okay, so 6.90. The power is better for an I 1.2 ampere ohm resistor is P equals to I square R. So you have 3.68 watt that power coming out from the resistor. Okay, so you can pause this video, you can try out. You have this example number 1. This example only has 2 EMF, and I think it only has 2 loops, so it's easy for you. I think you can do by yourself this one. So answer over here 1.0 ampere, 4.0 ampere, and 12 volt, 17 volts for the EMF E2. Number 2 over here we have 3 EMF. Okay, maybe you have 3 loops over here, 1 2 3 3 loops. Okay, so you can pause this video and you can try out 3.75 ampere current is resistor circuit. Okay, 1.25 and 1.25. It depends on how you label. You can label this one as I1. Also you can label this one as I1. It depends on your label. Okay. Okay, so we stop over here. Okay, and we're going to for the next time we're going to learn about potential divider. Okay, see you in next class. Bye bye.